So in today's video, which is in the continuation of the chapter Work, Energy, Power, having discussed work in the previous videos, today we shall talk about the concept of energy, particularly kinetic energy. Kinetic energy, as the name suggests, is the energy which is due to the kinetics of the body. Because the body is moving, has some kind of motion, it is because of that the body possesses some energy. So before we proceed, let's first look at the concept of energy itself. What is energy? Till now we have discussed work. We know that when a force makes a body move from its position, work is done, right? Force does a work. So what is energy is, we say, this is the very basic definition that we have. Energy is the ability of a body to do work. So if a body has no energy, it will not be able to do work for you. If it has energy with it, it will be able to do work for you. In order to exert some force, some energy is required, isn't it? If a body has no energy in it, it will not be able to ever exert a force and hence do a work, right? So we understand that energy is that aspect of any body, any agent that can do work, useful work, which we require to be done. So when we talk about kinetic energy as such, we say that kinetic energy is the energy possessed by a body due to its motion. Because the body is moving in a certain way, it can do work for us, and that work comes because this body contains some energy with it because of its motion, and it is this energy that we are calling as the kinetic energy. A classic example would be the kinetic energy of the wind can make these blades of the windmill rotate, right? So because of the kinetic energy of the wind, the work can be done on the blades of the windmill, and you can use this work in various useful forms, right? We generate electricity through this. So this is the type of energy which comes due to the motion of bodies. Now mathematically, if we want to define kinetic energy, we define kinetic energy from this expression. It says the kinetic energy of a body of mass m moving with a speed v is given by half mv squared, where, mind you, v is the magnitude of the velocity of the body, not the velocity as such. So v is the magnitude of velocity, or which we call as speed. It is the speed that we use in this expression, and in that sense understand that kinetic energy, just as any other energy, will be a scalar quantity as work is, because energy is a form of work. Energy is also a scalar quantity. Not just that, the SI unit of energy is the same as that of work itself. So the SI unit of energy is work, not work, joules, the same as that of work, it is joules. Okay. So this is the basic definition, the definition for kinetic energy that we shall be using throughout our chapter. Now, how does a body gain kinetic energy? How does it get kinetic energy? Just as we have said that a body which has a kinetic energy can do work for us, the reverse is also true. Okay. So when a force does work on a body, we say that it gains kinetic energy. We can check that from our already known things. We already have discussed how a force can create an acceleration, and an acceleration can increase the speed of the body, and now we understand that if the speed of the body increases, as a result of that, as a consequence of that, its kinetic energy will also increase, isn't it so? In fact, we can take this very simple example where we can take a block on which there is a force F acting. Under the effect of this force, if the block moves a distance s, can we say that the work done by this force will be F into S, simply F into S, because force and displacement are in the same direction, right? And now, as a result of this, if we assume that the body which was initially moving with a speed u finally gets a speed v when it has already covered a distance s, can we find out the the corresponding values here? For example, can we write F, the force acting on the body, as the mass times the acceleration of the body? So F can be written as ma into s, and now we can make a small modification in this expression. We can write, we can multiply this expression by 2 and divide it by 2. So we can write it as 2 by 2 into m into a into s, and this 2, if we take with this as, we can use the third equation of motion, v squared minus u squared is equal to 2as, and substitute the value of 2as from this equation, which is nothing but v squared minus u squared over here. so that instead of 2as in the numerator, m by 2 remaining the same, 2as will become v squared minus u squared, and now if I just open up this bracket, I will get half m v squared minus half m u squared. What is half mv squared? This is nothing but the kinetic energy of the body finally once it has travelled a distance s, and half mu squared is the initial kinetic energy of the body when it started off. So, can we write this expression as the final kinetic energy minus the initial kinetic energy, which if we want we can also call it as change in kinetic energy, right. So, it is because of this work done by a force on the body that its kinetic energy change will take place. In fact, this relation that we have worked upon just now is a very important, very famous theorem that we call as the work energy theorem. We shall be discussing it next. So, see that just as energy is the ability to do work, work creates a change in the energy of the system. When a force does work on a system, its kinetic energy changes. Okay. Now, the next thing that we can discuss here is that kinetic energy depends upon the frame of reference. We can recall from the last lecture that work is also frame dependent. Work depends upon the frame of reference from which we are trying to calculate the work, right. The same way, we can see that the kinetic energy of a body also depends upon the frame from which we are measuring that kinetic energy. We can take up an example here. Let us say we have this frame 1 space associated with an observer which is at rest. This frame is not moving at all, it is at rest, and there is an observer here who is observing this block, let us say of mass m, which is moving with a speed v. Can we say as observed by the observer 1, the kinetic energy of the block as observed by the first observer would be half m into v squared simply, right. Now, there is another frame frame 2 which itself is moving with a certain speed v dash. If the frame itself moves with a speed v dash, can we say that with respect to the second frame, the speed of the block will be v dash minus v? This will be the speed of the block with respect to the frame 2. This is a vector relation that we shall get, isn't it so? So, this is the relative velocity of the block with respect to the frame 2, and if we try to find out the corresponding speed, v relative magnitude of this will be the magnitude of v dash minus vector v. What we are essentially doing is we are trying to find out the vector difference of the velocity of the body with respect to the frame 2, right. This is usually what we will do when we have to get the relative velocity. So, it is this value of speed that you will use to find out the kinetic energy of the same block when observed by an observer who is standing in the frame 2 now and observing the block. So, can we say that the kinetic energy from the frame 2 will be half m into v relative squared, which will be half m into mod of v dash minus v whole squared. So, see that the two kinetic energies are different. Kinetic energy depends upon the frame from which it is being calculated. Next, we can now look at the work energy theorem, a very important theorem in the chapter. In fact, a little later we shall be finding out, we shall be deriving the law of conservation of energy from this theorem itself. Okay? So, let us see what the theorem says. The statement of the theorem is, the work done by all the forces on a system of particles is equal to the change in the kinetic energy of the system. Let us understand all the terms one by one. Work done by all the forces. We now know that on a system, on a body, more than one forces can act at the same time, right? So, when we talk about finding out the or using the work energy theorem, we have to find out the work done by all those forces that are working on the body. So, have we discussed this thing that if we want to find out the work done by multiple forces, we have got a few choices with us. One thing is, what we can do is, we can first find out the net force acting on the body and then find out the work done by that net force. That is one way. The other way is you find out the individual work done by each of the forces and then take their sum, the scalar sum, to get the net work done. You add all the works. So both ways you will get the same answer for the net work done by all the forces. Okay. Next is on a system of particles. Now we have seen this in previous chapters. In laws of motion we have seen that sometimes we can combine two or more bodies and consider them as a one single system while we study them. Thus we study the forces acting on them, we study their motion and all that. So this is always possible to take more than one particles together as a system. You can always work with one single particle or one single body also. For the sake of convenience here, for example, we have taken just one single block, right? So it's up to us. So but whatever number of particles or number of bodies we have considered together as a single system, we use this work energy theorem on the whole system together. So we try to find out all the forces that are acting on all these particles together, and we then try to use the work energy theorem. So work done by all the forces on a system of particles, or we can call it the system under study, which might involve 1 or 2 or 3 or any number of particles, is equal to the change in the kinetic energy of the system. How does the kinetic energy of a system change? When its speed changes, right? So as we have just now seen above, in this particular case, when a block is exerted upon by a force and that force does work on the block, the kinetic energy of the block changes, right? Because its speed changes. The same thing will happen even if we are talking about a system of particles together. We are taking many bodies together, right? And we have some forces acting on the system. So this theorem is nothing but just an extension of what we have just now discussed above for a single body which is acted upon by a single force. Now we can have multiple bodies together and there could be multiple forces acting on them. The expression will remain the same. See carefully, the mathematical expression for the work energy theorem is that the work done by all the forces is equal to the change in the kinetic energy of the system, which is nothing but the final kinetic energy minus the initial kinetic energy of the system. Here, mind you, work done by all forces means you find out the work done by the individual forces and add them up, or you find out first the net force and then find out the work done by that net force, where the net force is given by this. So you have both the options. Depending upon the situation, you can choose which option to work upon, which one to choose. Okay, so it's just a choice that you can make, depending upon the situation maybe. So for example, here we have this block, let's say of mass m, and there are multiple forces F1, F2, F3 acting on the system, and under the effect of these forces this block undergoes a displacement S. So we can say that the work done by F1 plus the work done by F2 plus the work done by F3 in the block moving over a distance S, undergoing a displacement S, we can say that the sum of all these works will be equal to the change in the kinetic energy of the block, delta Ke, which you can also write as the Ke final, the final kinetic energy minus the initial kinetic energy. A very important theorem. We use it in many questions. In fact, as I was telling you that we derive the law of conservation of energy from this theorem itself, we will understand this as we take some questions also, that all the questions that we generally do using the law of conservation of energy can also be done using the work energy theorem very easily. Okay. So the next thing is, the work energy theorem involves the work done by all forces acting on the body, including the internal forces, the pseudo forces, as well as any other force that we see acting on the body. So this is a very important point. Otherwise, when we discuss the chapter laws of motion, we saw that, we discussed there, that generally when we are discussing the motion of a body, we are trying to find out the acceleration. We don't discuss the internal forces acting on the system, because we say that those forces cancel out in pair. But it is not so when we are discussing the law of this work energy theorem. Here we need to take up the work done by the internal forces also, because internal forces sometimes they do work, they do a net work on the system. So we need to involve those cells. Then pseudo forces. If we are working from an accelerating frame, we need to incorporate the pseudo forces and the work done by them in the work energy theorem, and any other work that might be acting other than the external forces, we need to consider those forces as well and consider their work also while using the work energy theorem. Okay. So, having understood this, the work energy theorem, the statement of that, let us look at a couple of examples to get comfortable with using this theorem into questions, and we will see how using this theorem makes the solution of the questions easier in comparison to the usual method that we tend to use to solve the same question. So, I will just take a couple of simple questions which we can do otherwise also through other means also, but using the work energy theorem will simplify them. Let us look at them. So, there is this block, let us say. The question is, there is a block of mass 2 kg and it is kept on a rigid surface like this, and there is a forward force of 14 newtons acting on the block, whereas the surface being rough, the block is touching the surface, the mu value over this rough surface for the block is 0.2. So, from this information we can actually find out the frictional force acting on the block as the block moves. Now, the question is, starting from rest, find the velocity gained by the block in moving a distance of 10 meters. So, the initial velocity of the block is 0, and under the effect of these forces it travels a distance of 10 meters. We are supposed to find out the velocity or the speed maybe that the block gains in the process of traveling through this distance. Now, understand that you could have done this question by considering the forces acting on the block, the forward force of 14 Newton as well as the kinetic friction that will act on the block in the backward direction. You can find out the net force, and from there you can find out the acceleration of the block, and then you can use the third equation of motion, v squared minus u squared is equal to 2as, to get your answer here, right? But let us see how we use work energy theorem and get this answer in one single step. Just that we have to get the value of the kinetic friction here first. What is the kinetic friction acting on the block? It is mu times n. Understand that in this question n, the normal reaction of the block will be nothing but its weight itself, mg. So, this will be mu into mg, which will be nothing but 0.2 into the mass is 2 into g we can take as 10. So, this comes out to be 4 newtons, right? And that is it. Now, let us use the work energy theorem. Work energy theorem, when used in this situation, will give us work done by all forces, means there are two forces doing work here. One is the external force of 14 Newton, the other one is the frictional force. Work done by the external force will be positive because the displacement is in the direction of the external force, whereas the work done by friction would be negative because friction is acting opposite to the displacement. So, can we say the work done by the external force plus work done by the friction should be equal to the change in the kinetic energy of the block. This is the work energy theorem. Mind you, there are other forces like normal reaction and mg also acting on the block, but they won't do any work because they are acting perpendicular to the displacement. What is the work done by the external force F? It is 14 Newton, the force itself, times the displacement 10 meters minus negative of, the work done by friction is 4 into 10 with a minus sign because frictional force is acting opposite to the displacement. This should be equal to the change in kinetic energy, which will be the final kinetic energy, half mv squared minus the initial kinetic energy, which will be 0 in this case because initially the block is at rest. So, now we can solve this. This is 140 minus 40, that will be 100, is equal to half into m, the mass of the block, which is 2, into v squared. We can simply solve this for the value of v, which comes out to be square root of 100, that is 10, right. So, 10 meters per second will then become the direct value of the speed of the block in traveling a distance of 10 meters. So, see how work energy theorem is able to give us the same answer that we would have otherwise got using the equations of motion. Let us take another example. Example number 2 is, an object of mass 1 kg falls through a vertical height of 10 meters. and reaches the ground and gains a velocity of 10 meters per second in the process. Okay. The question is, what is the work done by air resistance on the object? Find out the work done by the air resistance, the force due to the air in the process of the block moving down a distance of 10 meters. This is a good question because I understand that had the block simply moved down under the effect of gravity, we could have easily obtained the change in the velocity that the block will or the body will undergo in traveling through a distance of 10 meters. Now they have given to you the change in the velocity that it suffers, right? So using that, then we have to find out the work done by the frictional force. So what is happening here on this body is that there are two forces acting. One is the force due to gravity, mg downward, and the other force is the force due to the air friction, Fa. Both of them will do work as the block falls down. The work done by gravity would be positive, whereas the work done by the air friction will be negative. And the total work done by the two forces will be equal to the change in kinetic energy of the block, right? So in this case, can we say that using the work energy theorem, can we say that the work done by mg, the gravitational force, plus the work done by the air friction, that should be equal to the change in the kinetic energy of the body? Work done by gravity as the block moves down, can we say it will be the force of gravity mg times the distance through which it moves down, which is given to be 10 meters. Maybe we can substitute the value of m also here itself, plus the work done by the air friction. We can just keep it like that itself because this is what we are supposed to find out. And the change in kinetic energy will be the final kinetic energy half mv squared minus the initial kinetic energy, which is 0. The body starts falling from the top, so initial velocity will be 0 and hence the initial kinetic energy is 0, right? Now let us solve this. M is 1 kg, so this will be 1 into 10 into 10, the first term, plus the work done by the air friction is equal to half into m is 1 into v is given to be 10 meters per second, 10 squared, right? And see that from here we can write the work done by the air friction as 10 squared by 2, that's 100 by 2, minus, when we take this term on the right hand side, it will be 100. 50 minus 100, that gives us minus 50 joules as the work done by air friction. Can you identify why we are getting a minus sign here in the answer? Work done by air friction is supposed to be negative, isn't it? Because the frictional force is acting opposite to the direction of motion of the body. So we understand that it has to come out to be negative, right?